Welcome to our webcast, Power Factor Testing Today. In this session, we'll be discussing how our understanding of the traditional power factor test has evolved and what are the new techniques we should use to ensure we get the most reliable results. My name is Yirto. I'm the Marketing Communications Engineer for Mega North America, and I'll be acting as the moderator for today's presentation. I will be supporting you on any technical issues or questions for our presenter during the session. On the right-hand side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red. You will receive a copy of this presentation afterwards, and remember, you can ask questions at any time, and I will interject them as we have time. Our presenter today is Jill Duplessis, Mega's Global Technical Marketing Manager. Jill is based out of Boston, and she's probably going to get snowed in this weekend. Thank you for joining us, Jill.
Thanks, Cher. Good morning from my side. I hope everyone is doing well. Thank you for taking time out of your busy days to join me. I'm hoping you'll find this informative. The topic, power factor testing today, is quite timely. There's been a lot of activity in the world of dielectric testing in the past couple of decades, actually, and now I'm seeing a major shift underway. The industry is making a move forward to expanded forms of power factor testing. So I'm going to focus on the migration and why it's happening. The roadmap for my talk looks like this. Before we jump in and start talking immediately about the test for assessing insulation, we'll talk a bit about the dielectrics themselves, their function, the criteria we use to evaluate their health, and particularly going to key up a certain electrical test parameter, which is dielectric losses. Then we'll talk about how, as an industry, we got to where we are today. I believe that sometimes looking back reminds us to keep moving forward. I'm focusing on 3 key dielectric assessment methods today. First step will be a traditional power factor test. We will review how a power factor test works, and I'll be candid about the expectations you should build around its use. Deficiencies are what promotes change, so this is an important part of the conversation today. This will lead us to the final part of the presentation, which introduces DFR testing, or dielectric frequency response testing. A narrowband DFR test is an intermediate test between a power factor test and a DFR test. It's a departure from a power factor test because we are repeating power factor measurements several times across a range of frequencies. When compared to a DFR measurement, not only does a narrowband DFR test have a more narrow frequency range over which we measure power factor, but a narrowband DFR test does not rely on an insulation modeling database like DFR does. So we'll talk about both these tests and their advantages, and we will also talk about the very important parameter temperature that you cannot ignore when you're doing power factor tests. And then finally, we'll pull it all together with a summary at the end. So here we go. Let's begin with a few slides about the insulation systems in electrical apparatus. So IEEE defines insulation as either a material, or it could be complex, it could be a system of materials, but the system should provide electrical isolation between 2 parts that will operate at different voltages whenever the asset that they're in is energized. So I have a simple illustration of a 2-winding transformer. So for example, when I energize this transformer, I'll have a high voltage winding at 1 potential, for example, 69 kV, and a low voltage winding at some lower voltage, for example, 13 kV. And the task of this insulation system of materials is to maintain so-called electrical isolation. So I would say that's an operative part of the definition. So what do we mean by electrical isolation? Well, it simply means that when I subject the system of materials to an electric field, to energy, that most of that energy ideally should be stored by the system of materials. If I measure this system of materials my resistive component of current through the materials should be practically zero. Now, if you think about maybe what the imagery that resistive current might be conjuring in your minds right now is conductivity. You know, okay, real current flow through these materials. Yeah, it's insulation. I don't want that. But there is another component to, or another aspect to a resistive current that this parameter represents. And that is when I subject these materials to energy. Yep, hopefully these materials are storing that energy, but some of that energy is going to be lost as heat and it will be unrecoverable. This is because there are polarization effects, physical effects happening in the materials when they're subjected to a field. So we're going to talk about polarization losses in a few minutes and their contribution to essentially losses, because I sub R component is what feeds the losses that we measure when we do power factor measurements. So dielectrics perform best when they are clean, when they're dry, when they're relatively free of voids, and also when they're used within the temperature range that they were designed to use within. In fact, if we look at the three main adversaries to a dielectric's good health, I mean, what can hurt the dielectric? Arguably, this is listed in order of, you know, which ones, you know, the top one is worse, and then so on. But I would say moisture and heat probably compete for the number one position. They're both very harmful to your continued good health of your insulation system. Oxygen is on the list as well. But dielectrics are going to fail, the insulation system is going to fail or, you know, otherwise reach its end of life whenever the stresses across the system either meet or exceed the system's ability to withstand that stress. So I really like this slide, so I've borrowed it here, because not only does it illustrate when you reach end of life or when you reach failure, but it also reinforces a concept that we have some control over when this happens. So I think it would be unrealistic to think that an insulation system would forever have a withstand that would follow this blue horizontal line, because that's the withstand it starts its life at. But with age and, you know, and condition, the withstand capabilities of an insulation system will deteriorate with time. So you can see if you follow this yellow curve down, we reach an impasse where it turns kind of blue, dotted versus green. If we allow and never do any maintenance or assessment of the insulation's health so that we know what kind of condition it's in, so that we know what type of maintenance it might need, then you could imagine that this yellow curve is going to continue to follow the blue line, and eventually it'll intersect with the gray line, gray curve at the bottom that represents dielectric stress. And when it does, that's when we reach our normal end of life. That's our normal life expectancy, that many years. If an incident happens in the meanwhile that raises the level of stress this insulation sees, and you can see where the red line, vertical line, intersects with this blue dashed curve, then you have premature failure. But we do see that, gosh, we can control this yellow line a bit and cause this curve to shift up via this green curve by assessing the health of our insulation and performing maintenance tasks when it makes sense to. So, for example, if it's wet and moisture, you know, severely ages insulation, so we care about it for that reason. It also lowers the dielectric withstand capability of the insulation system, and it could cause a premature failure via, you know, if you get too much heat on the transformer, it can cause the water in the insulation to evaporate, and that bubble, gas bubble, can rise through a winding and cause a premature failure. So we do care about moisture, and if we can recognize when a transformer is wet and dry it, then we can actually increase its withstand. And now we're following this green curve, and you can see that we've extended the life of the transformer. But also I would point out that we have control over the stresses the transformer sees as well, the insulation sees as well. Because we can, if we are aware of the condition of our insulation systems, we can actually target transformers or label transformers on our system and say, hey, maybe this thing isn't severely wet, but for whatever reason it's severely aged. And you know what? Even on a short-term basis, I don't want to overload this transformer. I mean, yeah, it might be 90 minutes that I'm talking about, but I don't want to do that because I'm aware of the condition of this insulation system, and I don't think overloading a transformer and therefore the temperatures it sees would be such a good idea. Okay, so the question then is, since the insulation is one of the key systems that has to be managed to extend, an asset's life, a transformer's life, then awareness of dielectric health is very important. It's important because it helps us make informed decisions about how to manage our asset. So how do we assess dielectric health? Well, since insulation systems support electric fields, we care about their electrical characteristics. I mean, after all, it's their electrical behavior that makes them conducive to serve as good insulation systems in the first place. So we want to measure some electrical parameters. And the two big ones are losses, dielectric losses, and capacitance. Now, capacitance is important and conveys a lot of necessary information that losses do not. So I don't want to diminish its value in your mind because I simply don't have time to talk about it today. But instead, I will be focusing on dielectric losses. I think conductive losses are easy for people to conceptualize. So instead, I want to spend a couple of slides talking about polarization losses instead. What are polarization losses? So essentially, there's a family of 5 different types of losses, and in each of polarization losses. And I wouldn't say that each one of these necessarily are so relevant to the type of materials that we traditionally see in insulation systems. But just so that you can get an understanding of the physical effects that take place in insulation systems or in materials when they're subjected to electric fields, I thought I'd just quickly go through 2 slides with the 5 families represented. The 5 processes of polarization can be divided further into those that are associated with fixed charge and those that are associated with mobile charge. So the first 3 that you see on the slide right now are those associated with fixed charge. So just to give you a sense of how these work, the first one on the left-hand side is what's called electronic polarization. So in other words, when you subject a material to an electric field, to a voltage, a test voltage, on an atomic level, what you're looking at is a picture of an atom here with a nucleus and then the electron rings around that. So what happens is that voltage that's applied to it, typically on an atom level, you've got your electron cloud, your rings. The first ring around the nucleus can hold up to 2 electrons, and then the next ring after that, if you remember this, can hold up to 8 electrons and so forth, and then from there on it's 8, 8, 8. And so you see a picture with, a full first ring because the first one has to fill up, and then the second one fills up before you get any electrons in the third ring and so forth. When it sees a voltage, what will happen is actually it will cause an electron or electrons from the outermost ring to jump a ring, essentially. And it's more quantum physics than anything else. But in doing so, you release light and work is done, so energy is released. So that's a form of loss. The second one, also probably not so relevant to the materials that we see in traditional insulation systems, but it's called ionic polarization. This would be where the entire atom now is moving with the test voltage. Now, the only way this is going to happen is that if that atom has a charge, either a positive charge or a negative charge associated with it. And when it carries a charge, it's known as an ion instead of an atom. So a lot of times, instead of atomic polarization, this is called ionic polarization. And here, since it has a charge, when you apply voltage, this whole atom is going to move relative to the field set up with the applied voltage. However, you see this more in materials such as crystalline materials like salt. So that's ionic or atomic polarization. The next one does have a lot more relevance to what we're talking about. It's known as orientational polarization. So here we're dealing with a polyatomic molecule that is a dipole. And dipole has a distinct negative, carries a distinct negative and then positive polarity to it. So here we've got the water molecule as an example. And when you apply test voltage, then what's going to happen is this water molecule will, or whatever the dipole is, it will form a contaminant, will rotate to align itself with the field. The negative part of the dipole to align with the positive part of the applied field, and the positive part of the dipole to align with the negative part of the field. In that rotation and that reorientation of its position within the material, there's inertia that opposes that movement. So as it rotates anyway, because the field is forcing it to, it simply means that since it's opposing inertia that wants to stop its movement, it has to work. And so we're going to give up, again, some losses. So these are all forms of so-called polarization losses. And it continues now. This family and these last two polarization processes are associated with mobile and trapped charges. So if you allow enough time to pass, because as I've been going through these so far, I've gone through three, I'm giving you these in the order at which they happen. So as soon as I apply a field, the electronic polarization would happen first, and then, some cycles later, then you have or not cycles, I'm talking about applying a steady field. So, sorry for that. I didn't mean a cycle. So with time, though, and a steady constant, imagine just a very, very slow varying field. If I keep that voltage applied in a certain direction, then the atomic or ionic polarization will happen, and then the orientational polarization will happen. And if I'm still applying that same field and I haven't reversed its polarity yet, then these next family of polarization processes will have time to occur as well. So the next one on the list is this so-called hopping polarization. Essentially, this would be created by localized charges. So if you can imagine a homogeneous material now and charge that can move just within the material but not from end to end of the material, so not across the entire material but just within it. Hopping polarization would be those charges that can move within that material, but then they get trapped and maybe spend their time there until the field changes again, at which time they may or may not move, or they may move back the way they came, and so forth. So it's a very unpredictable type of process. And the last one takes the longest to occur, and it's called interfacial polarization. Now here, this is in more of a complex type of a insulation system where you have more than one material, but it would be produced by the separation of these mobile charges that will meet together at the interface of the materials and form essentially like a wall. You could look at it. So in this example, in this diagram, you see that the positive charge in the oil would be migrating towards the negative applied field, while negative charge in the pressboard material would be moving to the left towards the positive applied field. So they meet together and form a barrier, so to speak, which then any kind of mobile charge or conductivity that would occur between these otherwise might be, the path may be changed and so forth. This takes the longest amount of time to happen, so you'd have to have a very, very slow varying field in order for enough time to pass that interfacial polarization would happen. So a long, slow, long time passing, slow varying field would equate to, frequencies that are, extremely, extremely low. So we're talking for sure, less than 10 hertz before you would see interfacial polarization process having time to complete. Now, when polarization losses occur, they contribute to losses that we measure when we do, for example, a power factor test. Each polarization process I've described has what we call a resonant frequency, and that's a frequency at which the process will contribute the most losses to the measurement. And since each one has a different frequency at which that occurs, it's easy to see that, gosh, this is going to be a power factor measurement that's changing with frequency. The resonant frequency is described as, gosh, the polarization process, whichever one it might be, just like, for example, interfacial polarization. All the charge meets at this, at this boundary and forms this wall, and just as soon as they all meet together, then the polarity changes and everything is happening in reverse direction. So it's that frequency at which the process has just enough time to take place, and then and then the applied polarity changes and the process starts all over again. So if there's never a resting phase to the process, that would be its resonance frequency. So I just give you that because I want you to bear in mind that when we measure loss, dielectric loss, for example, a power factor measurement, polarization losses are part of what we measure in addition to conduction and conductivity. So that's all I wanted to share with you about dielectrics. Next, I'd like to move on and talk about the migration to power factor testing. How do we as an industry
before we move on, Joe?
Oh, yes.
Can we take one quick question from the audience?
Yeah, of course.
Abbas wants to know if these polarization losses are only relevant to a DC voltage test or also in AC as well.
Oh, that's a fantastic question. So the answer is it's relevant to both. With AC, depending on how quickly we're varying the field, that will determine which of these polarization processes have time to take place. If the field is being varied very quickly, then the polarity is changing fast. Some of these polarization processes won't have time to take place, and only the fastest of the polarization processes will. So depending on what frequency we're operating at is going to definitely influence which polarization processes are, contributing to the measurement, having time to contribute to the measurement, and which ones are not. So it is a phenomenon that's relevant to this discussion about, AC testing, not just DC testing. But that was a great question because it kind of gives me a segue into then talking about how we ended up at power factor testing, because if we kind of go backwards and look at where we started, well then for sure first came the DC insulation resistance testing. And if you've ever done a DC insulation resistance test on a transformer, you'll know that the result is not immediate. You have to wait some bit of time before you reach stability. And that's because you're teasing out these so-called polarization effects. Once the polarization process is complete, then it's no longer contributing any losses to your measurement. So you will reach a point where you stabilize, and then you can get your true DC insulation resistance value. And so when we do a DC insulation resistance test, the goal is, hey, what kind of conductivity do we have in this specimen? That's the kind of information you're trying to determine. In fact, you've probably heard of the PI test, polarization index test, where you're comparing your resistance value after 10 minutes to 1 minute, and you don't expect them to be the same because you're still waiting for some of these polarization effects to kind of get teased out. So that was what came first. So the question is, well, gosh, why did DC insulation resistance testing? You still see it done in forms on transformers, but why is that not the predominant industry-embraced method to assess dielectric health on a transformer? So what are the problems? One of the problems is, well, by the time this test is effective, then you know that things are really bad with your insulation system. So if I take an example of a contaminant we worry a lot about, that's water. If you have a high enough concentration of water in your insulation, then it will contribute to conductive loss. which is the focus of your DC insulation resistance test. But at lower levels of water contamination, and albeit they're still completely unacceptable and not okay, at these lower levels, then water contributes to polarization losses. Because it takes quite a bit of time or things to advance, deterioration and, the situation to really worsen to a really bad degree before you recognize it with DC testing, the desire was there for, gosh, we need earlier detection of a problem. Another problem with the DC insulation resistance test is specific to a complex insulation system like you'd have in a transformer or capacitor-graded bushing. It turns out that it's not an effective tool to find a localized problem. So in other words, a problem isn't, prolific, is not spread throughout the entire insulation system, but just in a very localized area. This is a failure mode or a problem that we definitely want to identify, even more so than general contamination. Because if you have localized contamination, this is a weak spot in your insulation and it's making you very vulnerable to dielectric failure. So those are problems you want to react to immediately versus, hey, if my whole insulation system's aging and is general deterioration, yeah, I care about that, and at some point I'm going to react to that. But that's more a situation that you can monitor it with time. You don't have to react to immediately. A localized condition is a high concern. And DC insulation resistance testing, and on a complex system, doesn't have the ability to see that bad insulation. If bad insulation is in series with good insulation, it's still going to test good because conductivity will be, supported. It will be held to minimal with the good insulation. So it's hard to see a localized problem doing a DC insulation resistance test. So industry perception of a DC insulation resistance test on transformers, essentially it's looked at as a no-go confirmation test. You get the phone call, you have to respond, your transformer has tripped offline. You want a quick, rapid test that, hey, are we dead in the water here? Do we need to just implement a contingency plan here and then push this off to the side? We can do some diagnostics later and post-mortem tests, see what happened. So it's a good test to say, okay, no, it's past this, so now, let's start doing some other tests to figure out what exactly is going on. So it is viewed as a quick no-go confirmation, and it's also a good test to assess core insulation. The insulation for the transformer core is a simple insulation system, so actually it's a really nice test to assess, when I lift the core ground, am I getting this high ohmic read that I expect to get? And so it's a great test for assessing core insulation and whether or not you might have an intended core ground that shouldn't be there. So let's talk then about this shift to power factor testing, because along comes power factor testing with an AC voltage source at line frequency, and with this, your polarization effects never disappear. They never, you never reach a time when they're resting before, hey, suddenly you're reversing the applied field and the polarization processes start all over again. So because small amounts of water contribute to polarization effects, it was desired that they don't disappear so that you can detect small amounts of moisture contamination. Also, an advantage with the AC testing and going into this power factor test world was because of the difference between AC and DC, you could suddenly now detect localized problems in complex insulation systems with the AC. And this was very desirable to do that. I put a caveat in here, though, that if the measured system is small enough, because I will tell you, you have to be realistic. If the size of your insulation system gets quite large, your ability to detect a small localized problem, and we'll talk about this more in a few minutes, but it's going to get extreme. I would just go out there and say it's going to be impossible. So this is all, we can detect localized problems with an AC source, assuming that the measured system is small enough. So the industry perceptions of power factor tests on transformers. Let's talk about what those are for a minute. So I would say the industry at large believes it to be a very sensitive test for moisture contamination. I think people have maybe the majority has this impression that, look, if my transformer or my bushing passes this test, then my insulation is in good condition. I think there's also this perception that comparing to limits is an effective analysis tool. That if one is to manage the dielectric health of their assets through a power factor test program, that they're doing a good job managing the dielectric health. I think people believe that. I do think, too, that there is confusion with this test, that sometimes you can be left feeling like you aren't given enough information, particularly when your test results indicate that your transformer is not testing fantastic. So it's not bad enough that you say, oh, well, I know that's bad, and so I got to do something. But it's in that gray area where, okay, this isn't testing well. What do I know now? And I think people feel like, gosh, I still don't know very much. So just for a reality check, I would offer to you that it turns out a power factor test is not very sensitive to moisture contamination. Also, if a transformer or bushing passes this test using traditional pass-fail criteria, I would want you to know that your insulation may still be far from good condition. I do not consider power factor testing early detection of a problem. It's perhaps better than a DC insulation resistance test, but it's still, I would not describe it as early detection. And I don't believe that power factor is giving as good an overall awareness of dielectric health as the industry believes. So let's move and talk about each of these dielectric assessment test methods, the three that I had identified at the start. So let's talk a little bit about power factor. Other names for it, cosine theta, dissipation factor, tan delta. So there's many names, but all of these are referring to essentially the same test. To date, it's probably the most widely used electrical method to determine dielectric health of an asset. So how does this work? So say I have a transformer. I've shorted the windings to make them into like capacitive plates into these electrodes. So one of my, maybe I'm trying to test insulation between a 69 kV winding and all my grounded surfaces, 0 volts. So first thing I want to do is de-energize the transformer because it is a de-energized test, offline measurement. So I de-energize the transformer, so now it's sitting there, no potential on either side of this insulation. So I take an external source, a test instrument, and say I apply 10 kV to the transformer. All I'm doing in this is applying this AC voltage and measuring the total current through that insulation system. Now you might say to yourself, well, that should be 0, right? And the answer is no. Because in this total current measurement, I've actually got two components. I've got both a resistive current and a capacitive current. So remember, I'm putting a lot of energy across this insulation system when I energize this winding, and so that system of material stores that energy. So the capacitive component is a reflection that, gosh, there's a lot of energy being stored. It's the resistive component that I'm interested in. I want that to be, very near to 0. It would be unrealistic for it to be 0 because I have polarization processes occurring that are going to contribute to that measurement. And I certainly don't want, any conductivity through this material. Once I have measured via my test instrument that total current, the test instrument takes care of resolving it into a real and reactive component. So I don't have to do it. The test instrument reports back, this is the resistive current, here's the capacitive current. And once those values are known, and you can see them in these equations in red, then that makes possible the calculation of losses, dielectric losses, of your capacitance and your power factor. And I would just say that losses and power factor are very closely related. The reason power factor is used more often than dielectric losses as a parameter to assess the insulation is because it's taken out the size dependency of the insulation from the measurement. So in other words, if I look at dielectric losses, then I have to know exactly the size of the system I'm talking about. If I have a system that's 10 times as big as the one I'm looking at, then I don't expect the one 10 times as big to have the same amount of dielectric losses as, this other one that's a tenth of the size. If it's 10 times as big in the same exact condition, it would have 10 times as much dielectric losses as the one a tenth of the size. And when we were going around measuring insulation systems and apparatus, it's not that, we don't have the ability to quantify how big the insulation system is. We just physically can't access that information. And so that becomes a problem because if you're going to start doing some comparisons, you can't compare two systems that are not identical in size if you want to look at dielectric loss. The exception to that would be if you have previous test results for a specimen, then you can compare your dielectric loss to what it measured previously. But so power factor came along, and power factor reported a system's losses relative to its overall size. So power factor is relative losses, so suddenly I could take similar insulation systems that were different sizes and yet compare power factor results because it reported relative losses. So that was the value of that parameter. Power factor is simply describing how much energy gets lost by the system when we apply some total amount of energy to it. So how much of the energy we apply gets lost when, we energize the system. It's an index. It ranks the insulation system on a scale of 0 to 100, where 0 would indicate a completely insulating system, and it's reported in percent because usually the number is very small. So we multiply by 100 to deal in percent, so that is a more tangible measurement or index. Now, industry assessment approaches for power factor compare with previous. And then trending. Trending is the same as comparing with previous, only it infers that there's more than one previous result. So if you have 10 previous results, that's nice because, maybe you have an outlier, something that, a variable that influenced your power factor results that threw it out of whack. You can quickly identify which, are outliers that shouldn't be considered. So trending is nice. And then there's comparing with limits that have been established in the industry. Those are all methods to assess power factor. So deficiencies of power factor. So this isn't anything new. I think the industry has understood that, that this has been a deficiency for decades, really. But it's an averaging test. Okay, so what does that mean? Well, one, it impacts the ability to see a problem. So let me give you an example of another averaging index, and that is a class average. So if I was teaching a class and I have all these students, say I give an exam. I have 10 students in my class. 9 of the students get a 100 on the exam. 1 fails and gets a 50. My class average, the only index I'm provided as a teacher to understand how well my class is doing, how much they're grasping the information I'm teaching, is this average index. Well, my class average in that case would be a 95. And I might think to myself, great, everybody's on track. But I would miss the detail that, no, I have one student that's totally not understanding me. We're not connecting. And so, I would miss the opportunity to change teaching style and connect with this person. So I can't see that student. If I reduce my size of class down to 2 students and give that exam, and one gets 100, one gets a 50 and fails it, well, now my class average is a 75. So it tells me, gosh, it's not fantastic. I'd like it to be better. So I can see more information when I make a sample size smaller whenever I'm dealing with an averaging index. So power factor is the same way with insulation. It's why there's procedures available to always minimize the size of an insulation system when you're testing. That affords you the opportunity to see better. The only problem is if I'm teaching this class and I get a 75, I still don't know if I have a general problem, if both students got a 75, or if I have a localized problem, if one student got a 50 and one got a 100 or some variation therein. So I still am not able, no matter how small I make my size, unless I only had one student, right? But I wouldn't be able to determine if I have a localized problem or not. And if I make it down to one student, then it's not a complex system anyway, it's a simple system. Localized problems, it's important to be able to see that because they require immediate attention. Another problem with power factor is it's not acutely sensitive to problems at line frequency, and this is the frequency at which we have historically made power factor measurements. And even though the industry, I think, believes that it's very sensitive to, for example, moisture contamination, it's not. And I have a slide coming up to show you this. And so lastly, when a problem is indicated, it's impossible to differentiate and characterize a source. I mean, it always leaves you with this frustration of, gosh, well, why has my power factor changed? Because it can't be answered by just the power factor test. So this slide has a lot of good information in it. So what you're looking at is plotted on the vertical axis is power factor, or in this case tan delta. I got it from my colleague in Sweden. On the horizontal axis is my moisture in the cellulose in percentage, okay? So I've plotted out basically two transformers here, one that's in as new condition and one that's service aged. Okay, and so what this shows you is that one, the first thing I notice is that, well, they don't overlap. They don't have the same behavior, because what I'm looking at is what happens to my power factor as the insulation gets more and more contaminated with moisture. So as I go further to the right, how is my power factor reacting? So I would say one thing to look at is, gosh, let's take an example. I measure a tan delta in this case of 0.3%. So that's a green dot on that vertical axis. And if I just kind of dash line over to where that intersects with my service age transformer versus my new transformer, this 0.3% tan delta power factor that I measure in the field, that could be representing a situation where if I have a service age transformer, it's a 0.5% of moisture, and I'm talking moisture and cellulose, right, and not power factor. So, or it could be representing all the way up to a transformer insulation that's contaminated with 2% moisture content. Well, just to give you some frame of reference here, if I had a transformer that's testing above, say, 1.7% moisture content, then I'm not liking that so much. I would start targeting that as a candidate for a dry out. I mean, by the time I'm getting closer to 3%, I mean, that's where you're getting really wet. But yeah, 1.7 and above it's something that I would be not so happy about. And this is telling me that I can get 0.3% power factor for a transformer anywhere from 0.5% moisture content to 2% moisture content. Well, the problem is I'm doing power factor tests to determine how healthy my insulation is, and this is telling me that, gosh, if you don't have an idea of the condition that your insulation is, then it's really a moving target. You don't know how much moisture contamination you really have in the transformer. And you can see at the orange dot that, at 0.5% moisture, or 0.5% power factor rather, moisture is going to be somewhere around 3%. So that's actually quite high for a 0.5% power factor to be, representing something that wet. And so another thing I would point out about this picture is that the slope of these curves. You can see wherever it's relatively flat, the red and the blue curves, that's telling me that power factor isn't responding to increasing moisture contamination. So as I get wetter and wetter and wetter, I mean, there's some kind of response, but it's extremely small. So it's not until I get a steeper curve, and that maybe is happening somewhere, depending on which condition you're in, starting somewhere between 2.5% and 3% moisture content before you're starting to get the power factor index really starting to react in some kind of noticeable way. So that's pretty bad news for a power factor measurement, that it has to get that advanced in moisture before you're really seeing any kind of movement in your power factor measurement. So what kind of implication does that have then? Well, it tells me that, okay, my power factor has a lack of sensitivity to moisture anyway at 60 hertz. So that means that if I'm going to rely on power factor to assess how healthy my insulation systems are, then I better take any change in power factor seriously. But the danger there is, gosh, I don't want to be overreacting to every time I see a small change in power factor, I'm chasing down all these different possibilities, because a lot of the times it's going to turn out to be a false, reaction and a waste of time. Also, because of this lack of sensitivity, trending is going to be your best analytic tool, so that you can say, gosh, have I experienced any change? But if you're going to rely on change in power factor to detect a problem, and if you are going to take small changes seriously anyway, then the biggest challenge you're going to face is that you're going to have to filter out other variables that could be influencing your test results so that trending is meaningful. A huge variable on power factor testing is test temperature. So if you are not correctly compensating for the temperature at which you're performing that power factor measurement, then you're really, to think of trying to do trending and detect small changes in power factor, that becomes a little bit almost unrealistic. And there's other things listed here too that variables that could influence your test results, not in a representative way. At the end of the day, you want a representative power factor. So how do you get more from your power factor measurement? Well, you can further segment the system. There's all kinds of test procedures so that you can try to make them smaller so that your sensitivity increases. Or an alternative is to simply repeat power factor testing at multiple frequencies. And then this leads us into a discussion of narrowband DFR and DFR, which is implied that it's a wider frequency band than a narrowband is. I would say that out of these two, trying to do these further segmentation of the system would be diagnostic efforts. You're trying to chase down why, maybe try to figure out where the problem is. There is a known problem. You're trying to figure out maybe where it is in the insulation system. Then those can be useful. Megger does have a magazine that we publish, and there's an article about Southern California Edison and some of the work that they've done to implement further segmentation of insulation systems to diagnose faulted transformers. But routine method would be this DFR approach. And Southern California Edison has embraced that as well, and it talks about that in this series of articles too. So let's move on then to a discussion about what's called narrowband DFR versus DFR, how they're similar and how they might be a little different. So first, narrowband DFR. This is essentially just repeating power factor at multiple frequencies between, for example, 1 and 500 hertz. It's not to be confused with SFRA. There's a lot of valuable information at offline frequencies, and so it's given birth to, over the decades, to a lot of interesting tests. I think since SFRA is very well known in the industry, that it's easy to get confused between all these frequency types of tests. They're not the same thing. So basically, we're repeating power factor at multiple frequencies, and then when we're done, a curve gets fitted to the multiple power factor measurement points, and the curve is what gets analyzed. So just to give you an example, this would be what healthy narrowband DFR test results would look like. So on this linear scale here, you've got a plot for CH in black, CHL in gray, and CL in red. And so what are you looking for? Well, we're not discarding power factor at line frequency. That's still an important part of the measurement. So first thing we do, we look at the power factor at line frequency. In this case, we're between 0.28 and 0.33. So you consider that. And then you're also going to check and make sure that you have a non-negative slope of this line that goes through that 60 hertz power factor, line frequency power factor. So that's one aspect of the analysis. And then the next thing you're looking at is what I call the tail of these curves. You want to make sure that it's expected that as frequency goes up, the power factor is going to increase, but you don't want this dramatic increase in power factor with frequency. So you're just checking to make sure that this isn't shooting off to the sky. If it is, then that's going to be influenced by problems that are adding to polarization losses. And so then you have a little bit more information on how you want to go about exploring that. So this following gives you an example of a narrowband DFR on a transformer that had high moisture content. And so you can see if you look at the 60 hertz value, it's around 0.4%. But to the left of that, your negative slope coming into that value. So these are just a rough idea of how you're analyzing these test results. And then I have one example here. This is showing, because you can do this on bushings and other insulation systems too. It's not just transformers that were performing this measurement. In fact, I really like it a lot on bushings, the narrowband DFR. This is showing, these were some 230 kV ABBO plus C bushings at an industrial site. And so when this tester tested these, the H1 and H2 bushings on this transformer were really nice results, kind of in line with one another. But then H3 had what I was talking about, where, boy, the tail of it really does something abnormal looking. So anytime you see something like this and you say immediately, okay, well, gosh, what could be causing these higher than normal polarization losses? And with bushings particularly, anything that interrupts the kind of so-called test circuit could be cause for this. Anything that would contribute to, I don't want to come out and say PD, but something that would contribute to this so-called hopping polarization phenomena could be subject and causing these kind of losses. So in this case, what it turned out to be, if you look, this is actually just the very, very top of this humongous bushing. You can see the bolts around it, so you can't see the sight glass beneath that. But it had the top terminal looseness. In fact, you could see where it was starting to arc a bit, and the tester ended up tightening this down and repeating the measurement. And I have the results. I don't have it in the presentation, but it came right in line, in fact, with H1 and H2. So it's a really finds a lot of these types of problems with bushings. If you could imagine, maybe even a tap electrode not having a good connection anymore to its layer that it's tapped to. So benefits of narrowband DFR. So I would say that it provides earlier indication of a problem in the dielectric than we've been afforded all these years with just a single power factor measurement. And that's huge, right? So a couple things, and I like to emphasize this one. If you really think about it, it's important. But the second one, it confirms that a seemingly good power factor result really is good. Because I would tell you that there's some seemingly good power factor results that are not representing well they're indicating the system's good when in fact it's not. And so this testing confirms that, hey, the seemingly good power factor really is good. And so that informed decision gives you peace of mind, lets you sleep at night. It also will reveal when the seemingly good power factor, oh yeah, this looks good. No, it's really not good. From there, though, I won't paint false expectations. It's not going to say, oh, well, definitely it's wet, or definitely it's got high oil conductivity, and so it doesn't go so far as discriminating the source of contaminant, but it goes a far way in giving you a quicker indication of a problem and better informed decisions. It can also determine so-called individual temperature correction, which I want to talk about next. So power factor is not very sensitive to an emerging problem, but it is very sensitive to temperature. And so when we power factor test, we have to pay attention to temperature, particularly if you're going to institute analysis approach of comparing and trending. Differences in your temperature between tests have to be compensated if you're going to compare between tests. So we always correct back to 20 degrees C base so that we can compare apples to apples, because we know, as for example, if temperature gets really hot, that our power factor is going to increase. But it's only increasing because the temperature is hot and not because the insulation is necessarily deteriorated. There have been generic correction factors available in IEEE standards, upwards until 2010. But in 2010, those disappeared, and the following note shows up instead. So if you look at the bottom here, it says, experience has shown that the variation in power factor with temperature is substantial and erratic, so that no single correction curve will fit all cases. Okay, so what this is telling is that, gosh, you know, IEEE acknowledge that one set of correction curves is not going to apply for a transformer that's been, you know, operated really hard to its life, you know, at full load in very hot temperatures, as something that may be sitting at 30% load in a colder climate. So to then apply the same temperature correction curves to a power factor measurement you're doing, simply not going to do an accurate correction back to 20 degrees C base. So it throws in a variable and disrupts your ability to compare now. Individual temperature correction is a patent-pending methodology which takes the frequency response, you know, so we were doing this, for example, narrowband DFR or DFR, so doing power factor multiple frequencies. It takes this response and uses the response to estimate the temperature dependence. And it allows for a very accurate correction back to any temperature between 5 and 50 degrees C. If you're interested in learning about how this is working, Megger's Dr. Robolino wrote a good article in Transformers Magazine this past year, and you can find the article in there and learn more about how it's working. But I'll just end on with a temperature correction with two quick slides here to give you an example. So here is a correction factor for a sample that has 1% moisture concentration. I borrowed these out of Dr. Robolino's article. And it's showing you the temperature on the horizontal axis in degrees C, and then the correction factor. So, of course, at 20 degrees C that we're expecting to correct back to, the correction factor isn't needed. It's 1 because that is the temperature we wish to have a representative power factor at. But as we get away from that, you can see that a correction is required, and it shows you what that should be, whether, you know, we multiply the power factor by, say, 1.2 at, you know, 6 degrees Celsius, or, you know, we multiply it by, you know, 0.95 at 35 degrees C. But it gives you a correction curve. So I want to show you for that same sample, as its condition changes, its requirement for what kind of correction you apply to it changes as well. So same sample, but now it's just wetter, more wet. And you can see that, gosh, my correction curve looks nothing the same. I'd even go so far as to say that within a transformer, we've done studies and have determined that, and for some transformers, the correction curve you would use for, say, CH insulation is not the same that you should be applying for CHL. Is not the same that you should be applying for CL. They have their different thermal responses. So if you're going to rely on power factor, make sure that you eliminate this important variable so that you are comparing things and that you can see real changes in power factor from test to test. And I'll end this on just a short explanation of DFR and what this is. So to execute a DFR measurement, again, repeating power factor measurements, only the frequency band width is now larger than what I had been talking about with the narrowband DFR. Now we're going from 1 kilohertz down to 1 millihertz. The analysis is performed by software. The user simply has to execute the test, perform these power factor measurements just like you would a normal power factor test, and you also need to confirm insulation temperature. For this, you can use the top boil temperature, the winding temperature if you have that. The software is going to do all the work and will automatically find the best fit between what you measure and between an insulation model. And it does this by varying parameters that are going to affect the response of the insulation model until there's agreement between that and your measurements. And I'll show you a picture here in the next slide after this one. What do you get from a true DFR measurement? You get a very reliable assessment of the moisture in your solid insulation. It also provides you your conductivity of the oil. It does give you, too, your power factor at, you know, whatever measured temperature and an accurate power factor at your reference temperature, 20 degrees C. So you can see that ITC is integrated with, at least with Megger's solutions, with their DFR test. And then it will provide you a temperature dependency the temperature dependence of your power frequency power factor results. So this is all based on this XY modeling. I won't go so much into detail, but it's important that you understand the insulation system in order to have a proper insulation model to do this curve fitting. And this is XY model has been accepted by the industry. Essentially, you're trying to determine, for example, between your high voltage winding and the low voltage winding here on this cross-section picture, you're trying to determine the materials present. So you got oil, you've got some press board barriers, and you've got some spacers. How much of that volume between the two windings is each taking up? So this is a modeling that the curve fitting is based on. This next slide just shows you in this red curve an example of what a measurement looks like. So this is essentially, your power factor, or tan delta in this case, versus frequency. You may or may not be able to see behind the red curve, particularly at the lower frequencies, a little bit of a green curve. This is the modeled curve that the software is fitting to the measured curve. And at the bottom are where you get your results. You get, your percent tan delta, and in this case, of course, in the U.S. here, we get the power factor results at line frequency 60 hertz. It provides back a moisture in your cellulose, in this case, 1% moisture in cellulose, and it provides you your conductivity of the oil in picosiemens per meter. On this next slide here, and this is just giving me an indication that, power factor is going to be influenced differently depending on what frequency I'm doing a measurement, because I've got two things in, that are contributing. I've got conductivity and I've got polarization processes. And depending on which frequency you're at is going to dictate which of those two is likely to be dominating the measurement. So this is just showing you at any given part along the response which factor, which force is really dominating the measurement. This next slide, though, to me is really interesting and kind of winding up my discussion on DFR here. But what I would particularly note about this is DFR's ability to distinguish between moisture and oil conductivity as sources of increasing losses. So here you can see in this red circle, these are the 10, and sorry again from my Swedish colleague, but it gives you tan delta at 50 hertz values, and so essentially they're 0.5% for all three transformers that are being measured. Where in one case the transformer is dry, another it's absolutely wet, and the other is a service age transformer. And so what I would say is, at line frequency, you're not really distinguishing between these transformers. To you, they are looking exactly the same. But in reality, they're anything but. They're quite different. If you look at the curve in blue, that's your very wet transformer. It actually has 3.3% moisture contamination, whereas one of these power factor or tan delta measurements, also essentially 0.5%, is representing a transformer that is dry. There's only 0.5% moisture content in that. But its curve shape tells us that, look, this has high conductivity oil, whereas the green one is just representing a service age transformer. So added value of DFR measurements, well, now we're given that extra step where narrowband DFR couldn't tell us how much moisture content we had. Now, by opening up this bandwidth, combining with an insulation modeling capabilities, we can estimate moisture content in the cellulose insulation. It's not just for transformers. You can do this on instrument transformers, CTs, and bushings as well. We estimate the dielectric properties of the insulating oil, the temperature dependency, and then can use it as a tool to understand, capacitance changes, power factor changes in a traditional power factor test. Could be used to monitor dry out processes and impregnation processes. So just to kind of now wrap this all up and summarize, a traditional power factor test, I'd say, is not acutely sensitive to changing levels of contamination. It is sensitive to temperature. If you're going to still continue to rely on just a single point power factor result, I would tell you trending is your best approach for analyzing it. but your success is going to rely on you having representative test results. There's many variables that can influence your test results. You just need to make sure it's a representative value because you're going to be interested in small changes. It could be telling you something significant. So to do that, you need to properly correct for one, for temperature influences. To push past some of the limitations of a traditional power factor measurement, you can segment further and perform additional tests. But on a routine basis, my recommendation would be to do with your power factor instrument these narrowband DFR measurements if the instrument can afford that. DFR, there's two types of DFR tests, what we call the narrowband, and then what you would probably think of most when you hear dielectric frequency response, wider band of frequencies and an insulation modeling capability. Both will enable determination of an accurate individual temperature correction for your transformer that you're testing or bushing. Narrowband DFR specifically gives you earlier detection of problems, verify if seemingly good tan delta or power factor values actually are good, and reveals when seemingly good power factor values actually are not. It does provide you the ITC capabilities. And DFR goes further in that it can distinguish between the source of increasing losses that are noted and say, hey, this is moisture in the solid insulation, tell you what that is, or it's due to oil conductivity, and in all cases tell you both. So that concludes my presentation. I would end it. This is supposed to be an informative presentation, so I just want to inform you that Megger does have solutions for, as far as you want to take your power factor testing program. We have our Delta Power Factor Test Instrument all the way on the right of the screen that does provide the option of performing the narrowband DFR measurements as well. Megger's been in the, one of the front leaders for, with DFR. Our first instrument came out in 1995 circa. So we, are onwards to, I believe, up to our 7th generation of DFR test instrument. We have the IDACs that will do not only DFR, but if you wanted to do narrowband DFR or just power factor with the instrument, then this would be a possibility as well. And our newly introduced TRAX, which is a multifunction test set and has the capabilities of a lot of test instruments built into the one instrument. And with that, if you're still there, I'm going to pass the moderating responsibilities back to you.
Oh yeah, I'm still here. Seems like we might have a technical issue because I don't think you could hear me throughout the presentation. So, well, the webinar is officially concluded at this point, but based on feedback we had from last year's sessions, we're going to extend the Q&A session for, another 30 minutes to answer all your questions. So if you have any questions, please submit them now into the Q&A box. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We'll greatly appreciate it if you could take a couple of minutes to provide your feedback so that we can continue to improve future webinars. A copy of the presentation will be emailed to you in the next few days, and a recording of this session will be available on our website at megger.com/webinars in the next 2 weeks. Okay, so now let's get to your questions.